So I want to talk about some applications of representations of finite groups. This is the intended audience are those who don't know much about the representation of finite groups in the sense that while I want to get to the applications, I will just explain some of the first couple of chapters in a standard representation theory book, and I'll prove or sketch the proofs of some of the things that I see some mathematicians here that I warn already. They may be bored from this part. Everything will be really simple. I mean, oops. Did I start early or you are late? So everything is really simple and actually, in fact, very, very beautiful. This theory is a beautiful theory, and it's of course very important in mathematics. I'm going to concentrate on applications that are somewhere in the border of computer science, math, and combinatorics. But of course there are many important applications of this theory, the representation theory of finite and infinite and compact groups and so on. They are very important in lots of areas of mathematics. I'm not going to talk about it. I'm just going to talk mainly about applications that have to do with graph expansions. Not only graph expansion, I'll do some other things, but I mainly want to focus on applications of this theory to expansion of graphs, in particular of Cayley graphs. And those I want to show you, these papers which deal with the expansion of graphs over any group, showing that very few generators are enough to expand in every group. I'll define expansions for those who worry. This set of papers has to do with utilizing expansion and utilizing the fact that a group is non-abelian in a certain sense to show that expansion happens faster than what you expect or what happens in abelian groups. This paper is not about expansion. It has to do with fast matrix multiplication, the Kohn-Neumanns and their subsequent papers. Has to do with matrix multiplication, fast matrix multiplication via group representation. I want to explain the basic idea of this. I'll probably get here. And I have some plans for next week. Well, first of all, I don't know if I'll get here, but because Russell promised to slow me down. I want to talk about some papers that have to do with expansion in non-simple groups. We know a lot, and I'll survey these results later. We know a lot about expansions in simple groups, but I want to talk about expansion in non-simple groups and talk about this paper with Meshulam and some other things. And I just want to mention one big thing that I will not talk about. Maybe I'll change my mind, but I don't plan to talk about, which seems to be a really nice application of potential application of the representation theory for Lie groups, and that's papers, a series of papers of Malmali and Sohoni that have to do with proving lower bounds. We're proving that determinant or that a permanent cannot be reduced to determinant in polynomial size. Okay, so let me just start, and just to stop me, Russell is not the only one that can slow me down. Anybody can. It's really hot. So the basic notion that we will study to begin with will be group action. So we'll have G will be a finite group, and I'll always have n to denote the size of the group. And the first notion is the notion of group actions. What does it mean that G acts on some set X? And it's a very simple notion, and it's very familiar. What it means is that every element of G, every group element, let me call it omega, because I'll use X for elements of X. What does it mean that G acts on some set omega? It just means that every element X here is associated with a permutation pi X on omega in such a way, so that's a permutation, in such a way that it respects group multiplication. So what we want to have is pi X, pi Y equals pi XY. So let's start to see examples. The most basic example, and it's very important, we'll return to it, is when G acts on itself. So omega equals G. So we start with examples. The set is G itself, and the group acts by left multiplication. So what happens is pi X of Y is simply X times. Okay, and that obviously respects the group multiplication by definition. There are many other actions of groups on questions. I already hear. For example, if you have any subgroup H in G, then the group acts on the cosets of H mod G. So you can take omega to be the cosets, and then pi X of now a coset is YH is XYH. You move the cosets, you permute the cosets. We may need it later. Let's go to specific groups. We can take a specific group like Sn, and then, of course, it can act on itself, but it can act on other things. For example, it acts on just the elements 1 through n, just permuting them, right? So even though it's a big group, it acts on a small set. It just permutes the elements of n. It acts on pairs. And that's basically what we have when we talk about symmetries of graphs or isomorphisms of graphs. We permute the vertices of a graph, and we get another graph. That's a permutation of the edges of this graph. So it acts on pairs, on triples, and so on. And lots of other groups. And the fourth one, which I always like to give, just for those who've never seen, these are sort of very natural actions and very familiar, and you could invent them yourself. There is an action that when maybe in the first instant you see it and you didn't see it before, you're not, it's not obvious that it's an action. You think about a minute and it is obvious, but let me anyway give this example just to make the point that actions of groups can be complicated objects. This is a group. So here G is this group. Here G is this group. So what is this group? This is a group of 2 by 2 matrices of determinant 1. So this is A, B, C, D, where all these elements A, B, C, D are in FP. And the determinant AD minus BC is 1. That's a group. And this group acts on the following set. The set omega will be just FP union infinity. So it's P plus 1 elements. And the way it acts is as follows. The permutation associated with such a group element ABCD is ABCD. The way it acts on some element alpha here, or let's call it omega, so let omega be an element here, acts on omega, is by taking it to another element by this what's called fractional linear transformation or Möbius transformation. And you can see that you added the infinity because you'll be dividing by 0, and you have to take care of the meaning of infinity over infinity and so on. But anyway, it's a permutation of this. Every element gives you a permutation. And in fact, they respect the group multiplication. So that's an action. And one, given this example and lots of other examples you can imagine and invent, you can ask, well, what are all representations? How do they? What are all actions? How do they look like? What are all group actions? Even if you fix a group, can you understand the set of all actions of a given group? And the short answer is yes. And I'll give you a longer one. But the first question sort of to ask is something I like saying, and I think some people like it and some people don't like it, but anyway, I'll say it. Group actions are something very nonlinear. I mean, the group is, they are not linear operations. And if you want to understand something in mathematics, that's a thing that may be controversial, you have to make it linear because otherwise, you're stuck. So you have to make it linear. So how do you make group actions linear? Well, there's one trick that works. This one universal trick that's used all over mathematics is that if you have an action on a set, if you have functions on a set, then you immediately, or you have something, operation on a set, then you immediately look at the same operation, you extend it linearly to functions on the set. So if G acts on omega, and you have and f is some field, then immediately G acts on the vector space f to the omega. But by this I mean just the vectors of elements of length omega, or this is just a set of functions from omega to f. Right? What is the action? You just permute the coordinates, right? Okay. So since since you have this, if everything is clear, don't hesitate to stop me. For this set of lectures, yes. It's not necessary. You can talk about infinite, but yeah. So since you have now something linear. So G acts on this vector space. So we said we have here pi x, pi y. Also on this set is pi x y. But this is a linear set, so we might as well think of these acting elements, these transformations, as linear transformations, namely matrices. So we might as well think of these guys as elements in M. What is the size? So let's suppose that the size omega size d. So these are elements. They are permutations, but they are elements in. Okay, they are linear transformations. So now we are dealing. The action is the actions we are studying is a set of linear transformations that behaves like the group G. In other words, now we have a definition. So this mapping that takes x to pi x, we'll call it rho, and rho is a group representation, which is the right way we want to think about actions, is a group representation. simply if rho from G to is a group homomorphism. Okay, so that just means that rho of x, rho of y, rho of xy, which is exactly what we had here. Okay, so we have this family of actions, or this family of, by now we want to think about these all group representations. What are all group representations? That's what we want to understand. And in what sense do we want to understand it? Well, I don't know in what sense, whether it was clear or whether it was even the way people started thinking about it, but here's a way to understand it. The way we want to understand the integers under multiplication is you try to build them up from the prime constituents. So we know that that every element, every integer, I don't know, A is the prime, is the product of pi to the ei, where pi's are primes and ei's are integers. We know that there is always such a decomposition, so that's an integer. There is always such a decomposition. We know that it's unique. We know what are the prime elements. They are those that cannot be divisible by any other integer except themselves in one. So we understand it, at least in this very, very simple sense. We have the unique decomposition to elements that are irreducible, cannot be reduced further. And then that you find each one of them an integral number of times inside your original number, right? So as it turns out, this is true just in this very high level. The same statement is true for group representation. So we'll just start developing it, but every representation, doesn't matter how complicated it is or what you see in there, can be decomposed into a number of irreducible representations, and they are well defined. What are these irreducible representations? And each one of them will be found in that representation exactly some integer number of times. Okay, so let's see how do we go about building the irreducible representations. So you can take any such representation. So let's spell this out. So what is this? Representation, it's a mapping. So we fix the field. By the way, lots of the theorems I'll talk about will be true only for the complex numbers. In fact, most of them will be true so let me just write it. Characteristic of the field that does not divide the size of the group. We'll see where it's needed, and many things will be true even more generally. And there are theories that take care of the so-called Brouwer theory that takes care of the case that if it's doesn't satisfy this condition. But we won't get there. We'll do that just a simple theory. This is called the simple theory, but it's called the semi-simple case. There must be something simpler. Okay, so anyway, we fix phi, we fix f, we fix g, and we are given some representation, and may be very complicated, and we want to simplify it. So what is a representation? So we have our group elements. There are n elements. And each one of them rho assigns to it some matrix. This rho of x, and they satisfy this multiplication property. And now we want to simplify them. So how can we simplify them? Well, there are matrices that act on this vector space on f to the omega, on f to the d, basically. So, right, it acts, right. These matrices, so f to the omega, basically I'll think about it as f to the d. So they all act on this vector space f to the d, and one thing we can try to do to them is somehow to, diagonalize them, or make them, make them smaller. And the way to do this is as follows. So let me just say v is f to the d. So we want to make them all smaller. So they are not simple, or they are reducible. These matrices are simultaneously reducible if you have the situation that for some subset of V, which is not V, and which is not the 0, some non-trivial subspace of the whole space, you have the situation that rho of x, W, is contained in W. In this case, you found an invariant subspace. So in this case, so if this holds for every x in G, then we have that W is an invariant subspace. And you can see that in this case, if you have this, then in fact you have the span of all these of xw is exactly W, because if this is the identity element, then rho, I should have said, it's sort of obvious that if we have this property, then we have the product property here. If it's a group homomorphism, in particular, we have that rho of the identity is the identity matrix, and rho of x inverse is rho, sort of obvious. So the span of all these, the way the movements of W under these matrices is W itself, because we have the identity matrix in there. And so W is an invariant subspace, and you could hope that you could change basis so that you'll change basis, so you'll separate out the action of all these matrices on W and the action of all these matrices on the complement of W. And it works, although it doesn't work immediately. You have to think a little bit, or you have to apply Maschke's theorem. Which says that if you are in this situation, W is an invariant subspace. I should say G invariant, but we are fixing G, so invariant and non-trivial, like here, then there exists a U. That's the orthogonal complement of so over finite fields there may be several complements, and you may want to choose it carefully, and you can choose it carefully in such a way that U plus W is everything, is V. So that's it is an orthogonal complement, but moreover, and U is also invariant. So not only W is invariant, but its orthogonal complement is invariant. Why is it good? It's good because now you can do a change of basis and start diagonalizing all these matrices. So what this means is terrible silence. So is it too clear, or too? No, it's not talking about the people who
I haven't found a reason to slow you down yet.
Good. Okay. So we found that we can, if we have these invariant subspaces, we are not looking at the matrices right. We should move to this basis and change it so that, what this says is that the matrices, all of them together, act separately on W and separately on U. So what it means is that we can change basis. There's unitary base change. I don't know how to call it. Say Z. So that if we now look at these matrices here, let me continue here.
So there is an inner product and
there is an inner product, although I didn't, you don't need it at this point. You don't need it at this point. So let me, I won't prove it, although even though it's just one line. To prove this, that there is an orthogonal complement which is also invariant, you start with any orthogonal complement. And then you take the projection from V to W with respect to that other orthogonal complement, and you just conjugate it with all group elements. So you sort of average out so that maybe it's not clear, or doesn't matter. If you want to know later, I'll explain. It's a one-line proof. But if you do it at the right time, then you will get your name on a theorem. So there is a unitary change of basis, so that if we look at all this, so here we had rho, but if we now look at Z rho, Z inverse, the same matrices, the way what they look like, initially they were arbitrary matrices, but now they split, right? They now look like this. And this is, let's say, the W part, and this is the U part. Okay, so by this I mean that these are zeros. So since the rho split into this, action on U and action on W, we might as well write rho as, I don't know, tau plus sigma, direct sum, the direct sum of two representations. I mean, because when you do matrix multiplication, we know that, rho x, rho y is rho of x, y. This is also true in this basis, which means that, when you multiply these matrices, what is in this left top corner multiplies, and what's the bottom right corner multiplies. So we have tau and rho, so this, we can call this guy tau. So tau of 1, tau of 2, and this is sigma of 2, sigma of 1, sigma of n, tau of n. And of course, these are also representations, right? So tau and sigma are representations in the same sense. Okay, good. So that's a method to simplify representations, just like dividing by some number is a method to simplify an integer, and we can go on and on and on and on until we get stuck. So what happens when we are stuck? When we are stuck, we eventually had some other unitary. So after some basis change, we got the representation down. So we eventually wrote rho as the sum of rho I goes from 1 to some t. And each of these rho i's are irreducible. What does it mean irreducible? We cannot do this process to them anymore, so we got stuck. So that means that they have no invariant subspaces. Okay, some of them may be the same one, some of them may be different. That's what we'll try to understand next, but that's what. Okay, so you can do this process to every representation, so we know you can get prime elements. It's not at all clear that, if you do it in one order, you won't get something different than if you do it in another order, but it will not happen. We'll prove it. Okay, so that's where we are. Every representation can be decomposed into irreducible representations. So now we want to understand what are these representations. Questions? Yes.
Is it true that there is always one invariant subspace in which all coordinates are equal?
No. In the no. No.
But
Actually, good. I remember something I wanted to do just for Russell, and because you reminded me, I almost forgot. I want to do an example. So let me do an example. I hope I remember it right, but
just before the example, this direct sum between the representation is defined with respect to this z? Or
Z doesn't, if you take any representation, forget these invariant subspaces, take any representation that you, and do a base change, it will still be a representation that's essentially the same as the previous one.
Still be a representation?
Yeah, it's another.
You're doing this decomposition, so every time you use different basis, a different z.
Right, yeah. So after a change of basis, what you'll get is that the original representation, all these matrices, are just block diagonal. With 1, 2, up to t. You know, they will have some dimension.
It's going to be local, yeah. It's inside U or W.
Yeah. Oh, you recurse. Sorry, of course you recurse. You continue doing it to that's right. They will have some dimensions, and but yeah. Let me.
That it's unique.
No, it's not obvious that it's unique, but we'll see that.
It's obvious that if you start with a finite thing, that it stops at some point.
It stops at some point. Yes, it always stops. Okay, so now let me just do one example so that you see how this decomposition works, and you'll see that it's not always that you have this invariant space, which is all ones which you are used to. Most of our examples do have it, but not all. So let's look at S3 and look at its action on the first three elements, right? So there's let's write down I hope I'll have room here. So we have, what are the elements of S3? I want to just do this picture in the particular case. So we have the identity, we have 1, 2, we have 1, 3, we have 2, 3, we have 1, 2, 3, 1, 3, 2. How do the matrices look like? First of all, they are 3 by 3, right?
I think maybe it's better to take the board a little bit down.
Which board down?
The bottom one, just so it's not in the shadow.
So what are these action matrices? They are permutation matrices. So this is 1 goes to 2, 2 goes to 1, 1 goes to 3, 3 goes to 1, 2 goes to 3, 1 goes to 2, 3, 1 goes to 3, 3 goes to 1 goes to 3, 3 goes to 2, right? Okay, so that's a set of matrices. Anybody sees an invariant subspace? Madur? Yeah. So they act on. So we see immediately that all these matrices. So rho of x, when we multiply by 1, 1, 1, we get a constant times 1, 1, 1. We get 1, 1, 1. Right. So that's an invariant subspace. It's not empty. It's not everything. So it's non-trivial. So we want to find a good basis change. So what do you think is a good basis for the space, so that what is the right complement? What basis should I choose for the complement?
Did you decide the field already?
Yes. That's what you want to say.
With the sum is 0.
Yeah, so no. You're right that you need two vectors whose for both of them you need the sum to be 0. But you want a basis for this space for which, when you act with these matrices, it will be preserved. Okay? No, complex. So what Olga suggested is the right So the other two vectors we should take are these vectors. So these three vectors, of course, generate the space. And let me not do the, well, maybe I'll do one example. Let's see why is it a good space. If let's look what happens when you, okay, let's do O of 1, 2. Let's apply it here. So we just switch the two coordinates.
Omega to the 3 is 1.
What?
Omega to the 3 is 1.
Yeah, omega is the third root of unity, thanks. Omega cube is 1. Yeah, that's a third root of unity. So what happens when we apply rho of 1, 2 to this vector?
These two are not orthogonal.
Which two are not orthogonal? This and this? Why not? They are. They have to be. Yeah. You multiply like you multiply complex vectors. I'll keep forgetting to conjugate things, but yeah, when you when you do inner product between this and this, you get 0, right? Because it's complex inner product. Yeah. So when you multiply, so what does it mean? This is a transposition 1, 2. You switch the two elements. So this is omega 1 omega squared, and this is really good because this is a shift of this guy, right? That's I think this is W. Yeah, this omega times 1 omega squared omega. Okay, so what will happen after we do the change of basis? So here we have the usual basis, E1, E2, E3. We want to move to this basis. And after we move to this basis, what will happen? Well, what will happen? Let's draw them. Maybe you can tell me. We get the two representations, one of dimension 1 and one of dimension 2. Okay, so one will be of dimension 1. What will be written in these coordinates? So this is the representation that corresponds to action on this subspace.
So
The identity. So if this is our rho, and we write rho equal sigma plus tau, then we have sigma is the identity representation. It sends everything to every permutation to the constant 1. And what will be this guy? So you can start figuring it out. Of course, for the identity element, it will remain the identity matrix. But let's see, we looked at 1, 2, and we saw that what happens is the first guy moved to the second guy multiplied by omega, so you can check. I'm not going to do this. This will be omega, and this will be omega squared. And I think that when you do 1, 3, this will be the opposite, omega squared and omega. And when you do the last two, you get 1, 1. Okay? So that's the portion. I mean, I write it in blocks, but obviously they don't talk to each other. So there's sigma, which is a one-dimensional representation, that is the identity representation, and the tau, which is a two-dimensional representation, which you can figure out what should be here. Probably when we shift by 1, we shift down by 1, then we multiply by omega squared. So this omega squared, omega, and this omega, omega squared. I may have made a mistake, but you can check that the 2 by 2 matrices here, first of all, act just like the symmetric group S3. They just multiply exactly like they should. And another thing you should see, Madhur, is that this 2 by 2 representation has no fixed point. There is no invariant subspace. It's irreducible. So as it turns out, if you look at S3, you decompose it here to, you got two representations. Okay, let me not mention it. We'll get to it in a second. But anyway, here's a non-trivial representation that's not one-dimensional. Okay.
So, but you could have picked any other basis.
Yes. Yeah. So then the only thing that would have happened is that you may have gotten, this you would get anyway, no matter what you do.
Right.
And this you may have gotten this one under some basis change. It turns out, I mean, in this case, it's not problem to prove, but we'll prove it in general.
So why was I supposed to know to pick that?
No, you didn't, but you could apply the one-line proof of Maschke's theorem and some basis would pop out. You didn't.
Especially good, I guess, Russell is asking about this basis.
It's invariant. It's invariant.
No, but if I pick any basis, the space is invariant.
No. What do you mean? So take another basis, 1 minus 1, 0, and 1, 0, minus 1.
Right.
Right.
That's
And
what I was thinking of.
okay, good. So let's apply row of 1, 2. Sorry. So let's apply 1, 0, minus 1. Okay. So let's apply. So these are the two you pick, and let's apply row of 1, 2 to this.
Yeah. So you get 0, 1, minus 1.
0, 1, minus 1.
Which is the sum of the two bases, right?
Sum of the two bases. So in this case, maybe any would
No,
do.
but
It's,
any basis for...
okay.
If it's the same subspace, then...
If not over if we were working over some finite field, we would have a problem. We would have over the
So not any subspace, but once you pick the subspace, any basis is going to be...
I'm sorry.
What's nice about this is
You are right. The subspace. The basis doesn't matter. The subspace, it will be sorry. Here the subspace is uniquely defined, the orthogonal complement, and there is no problem with it. It's a subspace for which the sum of coordinates is 0. I'm sorry, I take it back. Yes.
maybe the nice thing about this basis is that all matrices are either diagonal or the opposite diagonal? Or
Doesn't matter. It's an example that you just to see this process in action. It's some people like examples and others don't. Okay, good. So, any more questions? So I want to, so I was hoping to blend enough applications in the middle of this, mini course on representation theory, but I can't do even the first one before doing, doing the full prime decomposition. I mean, it's not that I could do it without any of, but anyway, it will be more appropriate to do it after we have decomposed, we found the prime decomposition of all representations. So let me do it. So the two questions we asked, what are all the primes? Are they finite, infinite? Certainly there are infinite number of representations. So even for a given fixed group, there are infinite number of representations. So we want to know what are the primes, are they infinite, and we want to know whether the decomposition is unique or not. Right? And it turns out that the answers to all questions come from just one simple lemma. It's as simple to prove as Maschke's theorem, but it's called a lemma, and this is Schur's lemma. And it's, everything follows from it. It's sort of amazing. So you take two irreducible representations. So it basically, the message of Schur's lemma is that the space of representations is extremely rigid. There is no room for much. And I hope this will be clear. So we take two irreducible representations. So rho and tau are irreducible. Okay, they may be of different dimensions. So so in general, I'll use d rho to right. I'll use this notation when I need the dimension of a representation. So there are two irreducible representations, and suppose, later we'll see where these things come up, but suppose we are in the following situation. We have some linear transformation, some matrix A, and it's of the appropriate dimensions, such that okay, this is the same, this is an assumption. Okay. This is the same, I could have written it. Sometimes it's more convenient. So when you sort of pre-multiply A by rho of x and post-multiply it by tau of x, or the inverse, then you always get A. So you know, it's always fixed. It looks like a very special condition. We'll see later that we can generate it easily, but let's just assume that there is such matrix A. In this case, and these are irreducible representations, in this case we completely understand this matrix. What does it mean? We have either okay, sorry, I forgot to make one definition. So given what we've done, this basis change, let me just say here, let's draw the two representations are the same if you know, there is a unitary z such that rho is z. Okay, in particular, what?
What does it mean to be unitary with its finite field?
It's finite field. It's an orthogonal matrix. A matrix whose you know.
Does it
What?
matter that it's unitary, not invertible?
Yeah, it doesn't matter. It's invertible. You know what? Invertible. It's unitary. May matter later. Yeah, invertible. So at this point, it's invertible. Okay, so if tau is not the same as rho, the only way this can happen is that it there is nothing, you know, this cannot happen. The only case it happens is A equals 0.
So it's not an either, there is only one, so...
Well, okay, yeah. There's yeah, either doesn't, I meant there are two, you know, this theorem has two cases.
So
One case is that tau is different than rho, and then the other that let's write tau equals rho. Okay? Tau equals rho.
Is invertible or is 0?
Yeah, and then A is no, but that's not all. It's much more rigid than this, is what I'm going to say is absolutely crucial. Of course, you're right, it's invertible or 0. And something stronger than both is A equals lambda I for some lambda. It's what it's called a homotety. It's just a constant times the identity matrix.
Isn't it the inverse of
What?
A is identity and tau is the inverse of rho, then it's false, right?
No, they are equal because here there is an inverse.
Oh, then it's false.
Yeah. Okay? So
For the second part, you need the field to be algebraically closed.
for the second part, you need the field to be algebraically closed. That's true. I'll say, yeah, so when you are working with, maybe that's a general comment, there'll be lots of, yeah, it's good to have some representation theorists in the audience who can speak Hebrew also. When you are working, so as I said, most of what I've said, just if you want it to be absolutely true, although I'm sure there'll be mistakes there also, then think about the complex numbers. But when you are working over finite fields, to do this, you often have to go to the algebraic closure of the field. So you always should think that you are working over an algebraically closed field, and the characteristic of the field does not divide the group for this theory to work. Let's just see the proof and see where this comes. And it's just basically the definition. This is justifiably called the lemma, but it's the foundation of everything. And why is it so? So I'll just state it. I mean, you can just stare at it and check. It's the following. So you look at this equation, and you see immediately that the kernel of A is tau invariant. Everything that A makes 0 has to remain there, so that the 0 will be on the right-hand side. And similarly, the image of A has to be rho invariant by the same reason. And so, I mean, you see immediately that A has to be a square matrix if you want it. We know that there are no non-trivial invariant subspaces to these representations because they are irreducible. So each of these has to be either everything or 0. So the only way it will be non-zero is if it's invertible, right? And if it's invertible, already we know that tau and rho are the same representation. They are equivalent representations. And now, in the case they are the same representation, how do we see this? Well, A has some, so A is an invertible representation. If we are over a field of characteristic 0, then it has some eigenvector. And now you look at the, so now we are, so assume that A is invertible. So we are basically done with the first case. And A is invertible, and lambda is some eigenvalue. Then you look at the kernel of A minus lambda I, and it's also, you check, this is also an invariant subspace. And the only way this would be an invariant subspace is if, so that's invariant, is that's rho, well, now rho equals tau, and it's rho invariant. The only way this can happen is that, okay, so.
Could you slow down and just go through that slowly?
Yeah.
So why is the kernel of A tau invariant?
So let's look just at the kernel. So suppose you have some v, so that AV equals 0. Okay, so you have some vector in the kernel, so AV equals 0. Right. So V is in kernel of A. That means that AV equals 0, and so rho of x for every x. But this has to be the same as A tau of x V. So this has to be 0. How can this be 0? If tau of x V is in the kernel of A for every x. So it's invariant. And the same on the other side. Let's not do it. Okay, so the only way, so each of these therefore has to be the whole space of the two different dimensions. Well, of course, if it was rectangular, what?
Either the whole space or
0. So 0 is a case we take care of. So
look at the image. If the image is 0, or
if the dimensions are different, then
if the kernel is the whole space, then the A is 0.
Yes.
So the kernel has to be 0, so A has to be invertible.
That's right. And also the image has to be everything for the same reason. Otherwise, it was 0.
Right.
Right. So that means that they both have to be the same. So rows and columns have to be the same dimension, and A has to be invertible. That's the last option,
Okay.
right? So, but if it is invertible, then you see that rho of x is A tau of x, A inverse, and then they are equivalent. Okay, then they are equivalent. So we are down to the equivalent case, so let's assume they are equal. And then you look, instead of the kernel of A, you look at the kernel of A minus lambda I. That's also an invariant.
How do you go from equivalent to equal?
No, you just, I mean, might as well change basis. You don't go, you just say they are equal.
But if you change the, okay, one is the change of basis of the other, but
Mhm.
that doesn't mean there's a change of basis where they're equal.
You can write 2 equals Z rho Z inverse.
Okay.
I didn't.
In one of them, and then they become.
Yeah, you change. So it's just Russell. It just this is the second. I didn't say that when they are equivalent, then it's. I just said that if they are equal, just if they are equal. If now you take that to be.
If they're equivalent but not equal, then A would be similar to that of this diagonal.
Yeah.
Okay. Because then you could change or something. Then you get the same result for
If they are equivalent, I make them equal, and then I claim this. That's the only claim, that if they are equal, then...
If they are not equal, the statement is that equivalence is unique after a scale.
Yeah. But Russell, forget, I didn't say, this just says that if they are equal, then you have this.
But then there's a missing case.
That's, it's not, yeah, fine. Let's say there is a missing case.
Okay.
Yeah. The only way A is not 0 if they are equivalent. Okay? First of all, that we established.
Right.
And if it's not 0, it's invertible, and they are equivalent. And now I want to look what happens if they are equal. If they are equal, we have this. Okay? That will be sufficient for our purposes. Okay. So why does it give everything? So I just want to explain this. I'm going much slower than I planned, of course. I always do. So, yeah.
Another way to say that A has to be a constant. So if it's 0, it's 0. If it's not, it's some other constant. So, right?
Yeah, but I mean, the 0 case may be rectangular. The constant case has to be square. It's not... So why is this... where is the utility of this? Where is the magic in this lemma? I sleep so... Olga, you... sorry. Yeah. More questions. You can ask more questions. I just want to make sure that you listen to me when I continue. So why is it such a great lemma? Because, you have to find the right A to apply it. Well, where do you find such an A? They are not, they are not obviously around, but in fact, you can take any matrix B. Take B to be any matrix that you like, okay? And just write A to be the sum of x B of x inverse. Okay? Just define it. Okay? And of course, A satisfies this condition. So if we call this condition star, right? because, I mean, when you pre-multiply it by a particular, let me call it y, so it's not confusing there. Y. And you pre and post multiply it by rho of x and tau of x inverse, you get the same sum. Okay? So that's the standard conjugation trick. Okay, so A satisfies star. So we can apply, we can take any B we like, do this trick, and then it satisfies. Why is this useful? It's useful because we can now establish this, the orthogonality relations of the entries of the representations of this. Okay, sorry. There's one more thing I need to do. But anyway, this is how we will apply how we will apply it. So actually, let me just do it here. It doesn't matter. So what B should we take? Well, we take a generic B, or if you want, just span all generic Bs by just their different, by some basis. So let's just take B to be something which is 1 in the JK coordinate and 0 otherwise. And we'll do it to all j and k. Okay? And now suppose we look at AIL. So we look at A at some entry of A. A is defined this way from B. Okay, what? So let me just try to say what I'm. Maybe before I do it, I'll explain what I'm doing. We have these two representations of the group G. One is rho and one is tau. And maybe they are different. Okay? What I want to show is that when you look at so it's a vector of matrices, and that's another vector of matrices. But but here, this vector of matrices, you can think of it as if this is d by d. These are really d squared vectors. You take this is one vector, and there's another vector, d squared vectors. And if this is d prime, then you have also here vectors, right? Take a particular coordinate and look what the value is for all x. It's a vector, whose length is it's just a function from the group to the field. And what I want to show you is that all these vectors that are not obviously, well, essentially all these pairs of vectors are orthogonal. Okay, except when you take a vector with itself. That's what is going to happen. So that's what we want to show. Okay, so you take any two irreducible representations, you look at any entry of one, and you look at any entry of the other, or even of the same, and we'll see. And you take their inner product and you get a 0. And this will follow from Schur's lemma. So it's clear what I want to do. It's clear what these vectors are. So I'm going to look at rho ij. So rho ij is a function from. And I'm going to look at tau, maybe rho I. I'm not sure which. How did I pick the indices, whether I picked them right or not? Yeah, I think rho ij and tau kl. And I guess now I'll work over the complex numbers. I want to show that they are orthogonal. Okay, so that's what we are doing.
Well, generally, they're the same or orthogonal.
What?
Rho
Orthogonal.
is the same.
Well, we'll see when they are the same. Yeah, we'll see. But we'll just take two of these vectors and try to understand what their inner product is.
So, sorry, what are the vectors are, you look at the ijth place in each of the rows, in each of row x?
Yes, exactly. You look at the ij place, so this is You look at one coordinate in all these matrices, and that's a vector of length n. Yes, and you have two vectors of length n, and we want to show that basically all inner products are 0. Okay, so how does it work? So we are here. So I pick B to be the matrix that in the jk coordinate is 1. And I look at this sum. That's a matrix A. And what do we know about A? Let's first assume that rho is different than tau. Okay? And we'll later look at what happens in rho when rho equals tau. But then, when rho equals tau, A, everything is 0. A is 0. A satisfies tau, so it must be the 0 matrix. But what is happening here? What is happening here? Here we get, when we look at this product with this particular B, we get exactly this inner product that's written there. So this is basically rho ij inner product with tau kl. And it's 0. I now, you have to conjugate and you have to take inverses, but basically that's what you get. So all of them are orthogonal if tau is different than rho. And moreover, even if tau equals rho, the only case we get non-zero here is on the diagonal, right? And so we know that, in this case, rho ij and rho kl is 0 unless ij is the same as kl. I equals k and j equals l. Unless it's the same.
No. Why does the j equal the j?
Because of the transpose and the inverse. It's so if you do the same vector with itself, you get non-zero, and if you in fact we know exactly what it is. So let me write it down. I'm not going to do this calculation because it just will be confusing with the. It's a one-line calculation that you'd better do at home.
You could have picked again. You picked to do it IL. You could have picked to do it JK.
Yeah, you have to pick the right but you understand the trick. That's the important trick. Schur's lemma tells you that this matrix is either the 0 matrix or it's almost completely the 0 matrix except the diagonal. And then you get all these orthogonality relations. And moreover, what you get in this case, unless they are equal, and in this case rho ij is going to be exactly 1 over the degree of rho. And that's another calculation you can do because you know the structure, so basically you know the trace. But anyway, that's a small calculation. So the point is that when we have irreducible representation, now there is not so much freedom. You can see that you can already see that there can be an infinite number of irreducible representations. Why? What? Yes. So if rho 1, rho 2, rho t were all, maybe they are, were all irreducible representations. Sometimes people write it shortened irreps. If they are all irreducible representations, that their dimensions are d1, d2, dt, then we are already manufactured how many pairwise orthogonal vectors? How many? Right? That we already proved, so we already know that there have to be a finite number of irreducible representations. In fact, it will turn out that this is there is equality here, so let's do this. But is this clear?
Is this also true in the
finite field case?
Yes?
Right.
Yes.
The vector can be orthogonal inside.
Yes, but it's true.
No,
Yeah.
it doesn't follow from the argument.
No, it doesn't follow from the argument.
I'm sorry, why do we get DS now?
Because from every representation of dimension D, we got D squared pairwise orthogonal vectors, and they are also orthogonal to anything else of any other irreducible representation, right? So that's it. There's no more room for... so there can be only finite number of primes. So we know that they are finite, so we just have to find them, and now we are going to find them. Okay so far? Yeah.
Did you assume that they are equivalent? Or this was told for that are equivalent?
Yeah, they are not. So they are they are pairwise non-equivalent. So rho I, okay, But I don't distinguish equivalent ones. Okay. Yeah, you don't. It's just like when you work over the integer. It's a good analogy. You work over the integers. You don't distinguish p and minus p. You work over positive and negative numbers, and you factor. That's the same. Okay, it's the same. It's just a group of symmetries is a little richer, but it's all invertible transformations. Okay, so now we want to find all of them. And it turns out that you find all of them in exactly the place you would expect, maybe. And that's in the regular representations. In the regular. Okay, what's the regular representation of G? It's the one we started with. So it's I'll call it R because R of x is this matrix that we beforehand called pi of x. It's just a matrix that in position y and z you have 1 if and only if I guess x, y. So inverse is x, y. So y is the inverse of x, I guess, yeah. Okay. So just the matrix that corresponds to multiplication, to left multiplication of the group. Okay, so that's how it's. So what we did before, we took an arbitrary representation and started decomposing it. We can do it in particular to this representation. Right? So let's assume that we decompose it.
From what you just said, this is much too big, much too high dimensional to be irreducible.
That's right.
Every irreducible has to be at most dimensions square root of n.
That's right. It's much too big to be irreducible, so it will be reducible, and you start reducing. You also know that it's, for example, the vector all ones is for this representation. Yeah, so you start reducing it, and you get. And you get, so we said that these were all irreducible representations. We saw that they are finite, they are all of them, all in equivalent irreducible one. And you're right, so that means that R will be the direct sum of, well, like with the prime decomposition, let me write it additively, so M1, rho 1, plus M2, rho 2. And this is just shorthand to writing rho 1, rho 1, rho 1 m times. Right? Okay, so we're going to just prove that. So that's a decomposition we made. Maybe it's not unique. We'll show that it's unique, but it's one such representation, such decomposition of the regular representation, this representation, to a sum, a direct sum of irreducible representations. Here are all irreducible representations. Now we want to deduce something, and what we can deduce from what we just did, I'll do a little more. We need just a tiny bit more. Yeah. At least I want to get to the Fourier transform, but okay. Which we are almost there. So we decompose the regular representation, and now the claim is that all, in fact, I'll just write it for this. Mi equals di for all I. So remember, di's are the dimensions of these representations. So in particular, they are positive, right? They are integers. So positive integers. So all of the irreducible representations appear in the regular representation. In fact, each one will appear exactly with its dimension number of times.
And then you get the sum of the di squared.
And then we get, yeah, this will imply that this, yeah. Right. So how, okay. Now let me delay this comment to later. So let's prove this. Everybody is happy? Yeah?
No matter what G acts on, they're...
No, we look at G acts on G. The regular representation is G acts on G.
Yeah, but I mean, in the previous example, S3 did not act on S3.
Yeah, we took some, it was some other representation that we decomposed.
But they still, the same reducibles appear like both cases, or?
So whatever representation you take, the irreducible components will be among the ones that appear when you decompose. Yeah, they contain all the primes. They contain them, in fact, in this, exactly this number. Okay? And this, again, is really simple. And for this, we just need to do one more thing and look. This is to look at the traces of the representation. So trace is a very important operation. So we'll prove it in a second. This is, well, maybe I should erase my plan, and therefore you won't see all I promised you. I'll do it next time. So if we have, if rho is a representation, then we can look at chi-rho, which is the character of, it's called the character of rho. And the way it's defined is very simple, is if we have chi-rho of an element x is simply the trace of the matrix rho of x. Okay. What can we say about these characters? Well, anybody wants to say something about the characters of irreducible representations? Let's say that we have rho and tau are irreducible. What can we say about it? What? They are orthogonal. They are I mean, this is, so if, for example, tau is not the same as rho, then this is 0. Because what is it? It's just, trace is just the sum of the diagonal elements. Inner product is linear, so you just do it entry by entry for, each of the diagonal elements. So this is 0. Just by the orthogonality of these vectors, rho ij, and we get that this is 0. And moreover, another thing that we get from this part, from the situation that it is the same vector, and we look at the diagonal vector, the other thing that we get is that chi-rho. So let me define, I didn't define inner product, but I should define it. So if we have two functions on f and g from g to, let's say, c, let me define fg, just 1 over n, sum f g of x, and maybe we need to take the conjugate. So I just take the average. That's one convenient way to define inner product, in which case we get here 1. So they are really orthogonal. They are really orthogonal. There aren't so many of them, right? I mean, maybe there aren't so many. There may be less than n of them. The number of this number t, just because the sum of the di squared is n, you know. So if some of them are bigger than 1, then there may be less. Then, you know, t may be less than n. In fact, what is the case that t equals n? Maybe it's a good thing to just, yes. So we know already equality here. So t equals n if and only if g is abelian. So why is this?
Matrices are simultaneously diagonalizable.
Yes, matrices all commute. Because they all commute, there is a way to diagonalize all of them simultaneously by an invertible transformation, and then you get all of them are 1. Right, and that's the only case, because if you know, if the matrix, if the group is not abelian, then they don't simultaneously commute. Okay, so the number of characters here, and we'll get to this maybe in a little bit. There may be a few of them, maybe fewer than n of them, but they are all orthogonal. So why is it relevant? So let's look at this representation, and we know that we have this formula, and we can write this formula also for the traces, right? We can take the trace of this matrix, the trace of this matrix, so on. We can just take traces as linear operation. So we know that chi r, the trace of the regular representation, is m1 chi. Let me call chi I to be chi or I. Okay, so we wrote, in particular, we have this decomposition of the character of the regular representation. Now, somehow we know something about, so maybe you should tell me, what is chi r of x? What is the trace of the matrix, which is a regular representation of the element x in G? Well, what is it in the case that x is 1? N. It's an identity matrix, right? It's always, yeah. And if x is not 1, it's 0, because x, you know, multiplication by x moves every element. Okay. So if we now look at, so let's look at now, it's, where should I move? Let's move here. Remember, we want to prove this theorem upstairs. You already see the proof, right? Yes? Well, I take inner product with chi I. Yeah. So, like you said, chi r, chi I. Well, it's just this sum mi, mj, chi j, chi I, which is by orthogonality just mi, right? So on the one hand we get, but what is this? This is just 1 over n, the sum over all x, chi r of x, chi I of x, right? But chi r of x is non-zero only once, right? We just have to look at the identity element. And the identity element, so chi r of 1, chi I of 1. What is this? This is n. What is this? What?
DI.
DI. Just its identity. DI and this, well, over n, I guess. So mi equals DI.
And if you wanted to, you could conjugate chi of x. It's any way of doing that.
Yeah, it could. Yeah. Okay. So all the elements, all the irreducible representations occur when you factor the regular representation. Okay, so I think I'm close to an application. Well, let me just.
Is this also true in the final field case?
Yes.
It doesn't follow.
Yes. That's but yeah, it doesn't. Yeah, it's whenever the characteristic of f, you do everything in the algebraic closure. Despite the fact that you work over the algebraic closure or over the complex numbers, all the entries of all these matrices in the irreducible representation will always be algebraic. They will also always live in a finite extension of your base field, just because, general nonsense. So no, you'll get that. No, you will get exactly. You'll get equality. Yes, yeah. You get equality. So okay, good. So we know this, and now I want to write the Fourier transform and maybe do one application. We have half an hour. No, that's not bad. We didn't take a break. Okay. So everything is clear so far. So we prove that, by the way, this proves uniqueness also, not just, this. If there were two ways to write down the regular representation as sum of irreducibles, we'll just get a contradiction when we take inner product with the different chi-i's. So we got uniqueness. We got that the regular representation contains every possible irreducible representation, and the number of times it occurs is exactly di, if the dimension was di. So this would be towards the Fourier transform of Fourier analysis on non-abelian groups. What we get is the following. So we took the regular representation that was and we decompose it. So this we decompose it means we change bases, and we got etc. We got this decomposition, and this was row 1, row 2, row t, and the dimensions were d1. In fact, yeah, I didn't write it down correctly. If we have any representation here of dimension di, it will occur if row 1 has size d1, then there'll be d1 copies of row 1. And then we'll continue. Okay? So that's the picture. Every representation of some dimension occurs this dimension number of times. This works perfectly to give us the sum of squares is n, so which we already did. But another thing it does is, okay, so I want to talk about the group algebra, and let me do it here. We are transform, and the group algebra go hand in hand, so that's what we'll do now. So suppose we have okay, okay, fine. The group algebra. The group algebra is denoted in this notation, and it just points out that vectors, so basically functions from G to F, Therefore, not only a vector space, but there is multiplication that you can endow them with. How can you endow them, these functions, with multiplication? Well, you have multiplication of the group elements, and you just extend linearly, right? So in other words, if we have f and g, two functions, so we write their product, which is denoted by convolution, simply as so that's what happens when you extend linearly the multiplication of group elements to multiplication of functions. This at a point x will be the sum over all y, f of x, y, say g, y. That's just the standard convolution. So you have here a vector space, or you have a set that has addition and multiplication on it. It's an algebra. So that's why it's called the group algebra. These are the elements in it, just these functions with addition and multiplication. What are the okay, how do I want to ask this? What's the dimension of this algebra? How many generators does it have as an algebra?
Dimension?
Yeah, how many elements do you know, if I take a set of elements, so n, yeah, take a set of elements, so if you add them and multiply them, you'll get all these guys. So the dimension is n, the dimension of this algebra. So, and when we look at this representation,
If you add them and multiply, wouldn't we just one get like everything or something? Or it's
no, you get by adding them with coefficients in f, you can get any function. And yeah, the linear
I
dimension.
mean, you couldn't, if you allow multiplication as well, you couldn't get
No,
everything.
I don't have multiplication in f. Multiplication just in this sense. Multiplication does. So, so a really important message is that we should think not only of we should think not only of elements in the group as matrices, like these ones, like the regular representation. We can think this way also of every function. So what we have done with the regular representation, we represented only elements in the group, but we can represent any elements in the algebra of the group. And the way you do it is that this R of f in coordinates x and y is just in coordinates x and y. You write here f of x, y. Okay, why is this? First of all, I claim that this is consistent completely with the definition in the case that f was just 1 on one group element and 0 on the rest. But if you think about this, what is this matrix? This matrix just, let's look at the first column. The first column y is, let's say we put the identity here and here. The first column is just f. Okay? And then the other columns are just permutations of f, right? So there are permutations of f. And because of the definition, I guess, what you get is that, well, what do I want to write? So suppose I want to look at the regular representation of f. What do you think it would be? I want to think of this multiplication as we should, as convolution. To me, at least, it's always confusing, and you have to remember the indices and so on. What I'm saying is that functions should not be thought of as functions; should be thought of the matrices that represent them in exactly this way. So it's a redundant form. Yes, it's just. So what happens for group elements extends linearly, and that's true for every two functions. And this is really great because that's you have all functions represented as matrices. You have the algebra represented as a normal algebra that you are familiar with, namely matrices that you know how to add and multiply. You don't have to think of strange convolution. I don't know if it's... Anyway.
This is only true for the regular representation.
Yeah, this is a regular representation. I'm talking now about the regular representation. When we talk about the group algebra, we represent it using the regular representation. It's a... And now will come something that is already explained, but let me just say what it is. This algebra is n-dimensional, so that it's spanned by n matrices, but it has n squared degrees of freedom. So in the normal way we represent it, we are doing something redundant. However, when we move to the, when we change basis and we get it in this form, right? We see really all the, we see the algebra in its sort of naked form or beautiful form. Namely, so the same change of basis that moves R to the sum of irreducible representation does the same to all these matrices, just they are linear combinations of the others. So it does the same to all of them. So, so let's call this change of basis this Z, let's call it the Fourier transform. So we know that there was a linear transformation taking the regular representation to this diagonal form of irreducible representations. It does the same to the group algebra. So this is a Fourier transform. So I want to write it. Let's give it a name. So f hat of rho. So if rho is an irreducible representation, so f hat of rho is the coefficient of the Fourier coefficient of. Let me just say again. We had here a matrix. So here was f and other permutation of f. This was R of f. We take it via this change of basis Z, which is, we call the Fourier transform for a good reason, because it's exactly the generalization. So in the case of abelian group, it is the Fourier transform. It's what diagonalizes the matrix.
So R of f is the representation of G?
Yes, R of f is the regular, R of f is the regular representation of the function f.
But then the group now is no longer finite.
It is.
The group of
I didn't change the group. The group is G. The group is G. I look at all functions on G.
Yeah, but before we want the representation of the element of the group, but now the element will be these functions.
Yeah, I'm not moving to a representation of f of G. I'm just saying that I extend the representation, what I call the regular representation of G, linearly to functions on G. Okay? I do it in this way. That's the definition. This is the definition. So the matrix corresponding to a function, it just puts the function and its permutations on the column.
But then there's no theorem now for this R, right? It has nothing to do with the original representation theorem.
R is defined here.
It's just a
No, but it's not just, yeah, it is defined here, but notice that R of x is R of 1x. That's it. Right? So it's just an extension. It's just an extension of the definition of R to point functions to now it's defined over over.
This is linear, so
It's linear. Yes, it's the sum, the weighted sum. Yes, exactly. So if we had a matrix, then we get from it these block matrices, and what we call the Fourier transform of f is the values, these matrix values in these places. Okay? So we just get with what we call, so of f is just, this again extends linearly because this is a linear transformation, so it's just f of x, or of x. Let me write it. If I do inner product with an average. So it's just extending linearly, right? This for every x, so f is a linear combination of x's with this value f of x. So now the value in this little matrix will be f hat of rho if this corresponds.
It's the same value in all the little matrices that correspond to the.
Yeah, for every, that's right. For every, if we have a repetition, if we have the same row repeating several times, we'll get the same matrix several times. Okay.
No, you couldn't, but because you're supposed to have n degrees of freedom.
Yeah, that's
so you need to use
exact.
different values for the same repetition.
No, I don't. No, notice again, maybe I should have stressed it.
Right.
Every representation occurs, every representation rho 1 of dimension d1 occurs d1 times. This works to make sure that the sum of squares here is n, but in terms of degrees of freedom, you take just one of them. This is d1 squared, and then d2 squared, and indeed that's the way to see that the well, actually there is a theorem that I should state somewhere now. I start getting a bit messy on the board. It's not clear that it continues reasonably. So let me state this before we proceed. So that's the Wigderson decomposition. It just says that f of g, again, we are in the semi-simple case, is, so we again have rho 1 up to rho t are the irreducibles. They are of dimensions d1 up to dt, is the direct sum of m di of f. Well, I guess f is algebraically closed still in this. Okay, so we have this decomposition. We take rho 1 once, we take rho 2 once, and so on. Each of them is, using this, extending the regular representation to functions, and then diagonalizing it according to the Fourier transform. Then we get little matrices for every f. These are the little matrices, these guys, right? For every representation, we can look at all possible functions and see what value we get there. What the Wigderson decomposition tells us is we can get all possible matrices. All possible matrices. F of g, this matrix algebra, decomposes into the direct sum of full matrix algebras. These are, so in every such square, when you run over all functions, f on the group, you get all possible matrices. And this completely explains the dimension of the dimension of the algebra. This algebra is dimension n, but these are n by n matrices, so there's, they are obviously special. In fact, we see that, there is redundancy here. If we have a vector here, then it's just permuted in the other columns. But after this change of basis, we see completely where the n degrees of freedom are coming from. There are t full matrix algebras. They are of dimension di, so we have these n degrees of freedom are coming exactly d1 squared for the first representation, d2 squared for the second one. They are full matrix algebras. Okay? Okay. So questions? Or,
So by this definition, the number of Fourier coefficient is less than n.
yes, it's less than n. It's less than n. So what is, that's very good. If you remember, when you look at every matrix, and you look at the different coordinates of the matrix, the vectors that they represent as you move over the whole group, this rho ij, are an orthogonal system of n, of exactly n orthogonal vectors. So that's good. They decompose the whole space of functions. But when you look at them as matrices, you have fewer, indeed, you have fewer than, In general, you have fewer than n. But each of them is a matrix. So totally you have all the information, but it's represented differently. That's why. Okay, so yeah, I'm just wondering if I can do for you one application.
Excuse me, it's not uniquely defined this way, it's not so far. Is there a canonical choice for this? Because you can still...
Yeah, fix the base. You're right. Fix the yeah, that's right. It's not canonically defined. For each irreducible representation is never canonically defined. So you pick one basis for it, for each of them. That's right. Yes. So...
you might point out that there's some beautiful number theoretic things that come out of the fact that the sum of the squares. For instance, we found a 1 and a 2-dimensional representation, but 6 is, so 2 squared plus 1 squared only gives you 5. So there's one more one-dimensional.
Yes, in fact, I wanted to point this out. That's very good, but I was going to point it out just immediately after I do the characters. But anyway, it's a great question even now to ask you what is the missing representation of S3. So S3, yeah, the sign, right? Yeah. So the missing representation is what sends an element. It's a one-dimensional representation which sends a permutation to its sign. So it's either 1 or minus 1. And so it's one-dimensional. We have 1 squared plus 1 squared plus 2 squared is 6. So you can actually, knowing these facts, in fact, the orthogonality of characters, we can maybe I should say the computational complexity. If I give you a group represented by a truth table, just the multiplication table of a group, it's not completely obvious. In fact, it's not obvious at all how to compute the irreducible representations. So irreducible representations are known explicitly for very few groups. But if you have your strange group that you concocted, then maybe it's not obvious what its representations are. But there is a polynomial time algorithm due to Baba and Ronier to find all the irreducible representations of a given group. And so polynomial time is polynomial in the size of the group itself, the truth table of the group.
You find an invariant subspace, or it's if you find an invariant subspace, then you can do it, right?
That's not the way you do it. That's not the way. Let me not get into this. Maybe I can tell you about this, about induced representation and so on, some other time. I just want to try to show something, and I'm not sure I may have everything I need for it, and maybe not. I just want to show an application. So let's see what we have. I think with this Fourier transform, maybe I'll need the inverse Fourier transform, but let me just do an application. Maybe I'll have to do it again next time. But so I want this application is sometimes called the Gauer's trick, and sometimes it's called well, okay. Some people call it the Gauer's trick. What is the Gauss trick? The Gauss trick has to do with estimating the rate of convergence of a random walk on a group, and in fact an inhomogeneous random walk. So you have two random variables, let's say two distributions, P and Q distributions. On a group G, and what you want to estimate is how quickly do you converge to uniformity. So what you want to estimate is what happens when you take P and then you take Q. So you take a random step in P and then you think of them as matrices. How fast do you converge to uniformity if you know how close to uniform P is and how close to uniform Q is. Okay.
What is the walk?
You take, so you pick an element, an element at random from P, and you pick an element random from Q, and you multiply them. Okay, and that's a distribution. Okay, so
The norm here,
but that's L2 norm. Thanks. There are results on other norms, but so there's an obvious bound that holds for every group that you can calculate, and that's square root n here. And what Gowers noticed, sorry, that's not Gowers, but this is, so this result is, as stated, is a result of Babai, Nikolov, and Piber. Is that you can write here, you can shave a square root m factor. So non-abelian groups, the convergence of such works is faster, where m is m of g, is the minimal di, where d rho, a rho irreducible, and rho is not a trivial one. So there is always, in all groups, we have the trivial representation that sends all elements to the identity. If you forget it, then look at the minimal dimension of a representation, and that dimension is something that you can put here. Now, it's, you know, if you don't have any intuition about these things, it may look, you know, maybe why should you care? This turns out to be so. Yeah, if I really talk about this application, I will not do it. I will do it. I will need more time. But this is absolutely critical because in several works, because well, I guess Gauss' motivation was for arithmetic combinatorics. What he want? Well, I'll just tell you about it. I will prove it next time. I think that's. So let me just tell you a few things. What? It can be tight in the case, you know, certainly in the case of m equals 1, it can be tight. And yeah, it's tight. It's tight. I mean, I don't know if for every group it's tight, but for lots of groups it's tight. For SL2P it's tight, and so on. So,
like, is this different if Q is like P to the K or something, or it's?
If Q is. No, it's interesting also to take the same distribution for both. It's not, I mean, it's just more general. Yeah, that's right. And you can iterate this, and you get an iterative bound. It just, in many, or in some proofs of expansion, when you do a proof of expansion of some random walk on a group or a Cayley graph, on some group, what happens, at least with the methods that we currently know, which are arithmetic combinatorics for, I erased already, but results like Gambo-Tsarnak on several groups and Gambo-Tsarnak and Schur, and so on, is what you can prove using some methods and some properties of the group, is that you can converge to a distribution that's almost the size of the group. That's, you know, the tools work in such a way that you can sort of, not easily, but with different methods, but easily, let me write it, easily prove that, get to a situation where P minus U is something like, this has to know, it's something like squared, let's say, is something like 1 over n to the 1 minus epsilon. You just, it's not uniform. It just occupies about, you know, the mean entropy is, okay. So you occupy n to the 0.9 of the space. You have expanded to occupy, what?
P minus u squared, to be that, you have to be...
Let's say you are uniform on n to the 1 minus epsilon of the...
Then that's going to be much bigger, isn't it?
No.
Because you're going to have, you know, say you have n over
two elements where you have probability 0, just those contributions to the.
No, it's, I mean, in general, if you have,
It's a probability.
if you have, you know, L2 norm 1 over S, then you are uniform on some S element. You can think that you are uniform over S elements, right?
L2, it's P minus U, right? So that's why it's
Yeah, think of, if you want, think of,
different supporters and the uniform.
this is this plus 1 over N. It's, yeah. Okay, so just telling you, you can get to such a
P squared
situation.
is like with the sum of the pi squared.
Pi squared, yeah,
Not
this
with
just
the
is
expectation in this one.
sum of
What
P.
is P here?
P is some probability distribution. Some probability distribution on the group. So I'm not telling you where it's coming from, but I'm just telling you that there are certain situations where you can get to a probability distribution over the whole group, which is not uniform. It's not even close to uniform. It's just you know, supported on n to the 0.9 of all the n objects, all the n group elements. But then, if the group is such that this m is bigger than n to the 0.2, is bigger than, you know, n to the 2 epsilon, then in just one more step, you convolve these two distributions with each other once, and you are already uniform. And that's something that doesn't work for abelian groups, and it shouldn't work for abelian groups, and it's critical for all these proofs like, so I mentioned Bourgain and Gambart proving that in SL2P, if you take two random elements, they are expanding. Let me say one more point that, because that's basically the end, just one more point about more generally how the decomposition of the group algebra is related to expansion. This, I'll elaborate about it next time, but let me just spend 5 minutes on it now. Since we are talking about distributions, I just want to point out that you know you are friends of elements of this group algebra when you represent them in matrix form. So let's assume again that we have some distribution on a group, and the most typical distribution we like to work with is this distribution of we have some S inside G, a generating set, and we look at the scaly graph of G with respect to S. So we connect elements if we can move from one to the other using elements in S, and the probability evolution matrix, the normalized adjacency matrix of this graph is a member of the group algebra. So I claim that the element of the group algebra corresponding to S is just 1 over S sum x in S. X, which just means that when we write the matrix, the transition matrix of this graph, the normalized transition matrix of this graph, so S here is the size of S. If we write the probability transition matrix of this graph, what we get is in position, I guess, y, z, we have S, we have 1 over S if, or so we have 1 over S if y z inverse is in S, right? So this is a Markov, the Markov process, or the normalized adjacency matrix of this Cayley graph. And what do we want to know about this Cayley graph? Typically, we want to know that it's expanding. What does it mean that it's expanding? We want to know that except for the top eigenvalue, which is obviously 1, all the other eigenvalues are small. How can we know the other eigenvalues? I mean, in general, it's a problem. And also in the case of Cayley graphs and groups, it is a problem. But we have this representation theory that tells us, look, this matrix is a member of this group, of the group algebra. So this is an f of g, right? It's a matrix exactly of this form. You have the entry is determined just as a function of y z inverse, right? It's basically yeah. This is the f. That this is the r of f of, and now after we diagonalize it, the eigenvalues don't change. So we can look at the eigenvalues in the diagonalized form, and then we can, we can and we should, so we just simplify it. We move to, here will be the 1, and here we have these representations, and we look for the eigenvalues of this matrix after the linear transformation here. This helps in many ways, more ways that that I'll explain. But one particular way that's related to what I said here about the where was it? About this, the way it helps here, and that will be the end, is that every representation occurs the number of times as its dimension, right? So what does it tell us about the eigenvalues? Assume that all representations have dimension at least m. What does it say about the eigenvalues here? Each one of them, each eigenvalue that appears with multiplicity m. And this multiplicity of appearance of the eigenvalue is the source of this m in this result. It's the source of this kind of it's a trick that appeared many years ago in a paper of Sarnak and Schur. They were the first to point out the power of this multiplicity in analyzing random walks and eigenvalues, and they gave an elementary proof of theorem of Selberg using just, almost only this. A weaker bound, but this was a proof that had a heavy number theory in it, and a much simpler proof was given using this eigenvalue multiplicity. So, no. The eigenvectors are not the characters. We'll talk about the characters next time. So now questions. Yeah.
So there is a general theorem. There is this bound that every connected graph has certain eigenvalue gap, and if you know that all the eigenvalues have multiplicities at least m, then the gap is bigger.
Yes, it's something like that. Exactly. Yeah. Basically, if you do the trace method, so you try to estimate the eigenvalue by, looking the second eigenvalue by just looking at the trace, looking at the sum of powers of the eigenvalues. If you know that the one closest to 1 appears many times, then it couldn't be too close to 1 if this, you have the bound on the number of walks. Yeah, so you gain by this. That's exactly where the source of, anyway, I'll show you this proof. It's 5 minutes, but I think I need another 5 minutes of background, and that will probably be 10. And anyway, we are not in a hurry, so we'll continue next time. Probably I'll do 2 more times. Thanks.